Thank you for having me. I am going to talk about our embodiment, our approach to this really high temperature thermal storage concept, this whole area. I'm going to do less display of results and more so talking about the logic behind how it is that we've envisioned our system and why, what the choices are, the design choices we made. And hopefully, leave some time for us to have some questions. Let me try to start a timer so I can leave a little bit of time at the end. So very simply, I think this is pretty obvious to everybody here, but basically what we're doing is going from electricity to heat, and then heat back to electricity. From a conceptual standpoint, this would sound like a really dumb idea because you're going to lose. We spend so much effort trying to convert heat to electricity the first time, and we pay a big thermodynamic penalty. So why would you ever want to do it twice? And I say all this because this is really to highlight, at least from our point of view, the whole logic behind this. The whole essence of this comes down to the fact that there's one real advantage to storing heat, which is that it can be much cheaper. So the only true advantage you get with any of this is the fact that the storage of the energy can be 10 to 100 times cheaper than storing it electrochemically. So that's the main thing we're leveraging, and then we're paying a whole bunch of other losses. We're dealing with all kinds of complexity, all kinds of new issues, just to get this one benefit of storing electricity much cheaper, or storing energy much cheaper. So I'll say that from that perspective to then give some context to why we chose the materials we're choosing and why we're operating it the way we are interested in. So from a very fundamental level, I think it's important to point out why is it cheap, why is it so cheap in the first place. From the perspective of thinking about, let's say, a battery from an electrochemical perspective, you have an arrangement of two materials that want to react. You put in between something that prevents them from reacting and only allows one of the key species to ionize and go through. And this, at an atomic level, means you have to organize the atoms. You have to get them all in the right places. And the number of atoms in this entire box that are actually participating in the energy storage is quite small. And as a result of this, you can end up with high energy densities because there's a lot of energy per atom that's participating. But the costs can be high and the lifetimes can be low because they're rather sensitive to deviations from this structure. So if the battery heats up or if it gets side reactions, these kinds of things can damage it. And so it's not particularly very robust from a very intrinsic perspective from the beginning, just the way that it's set up. Conversely, on the other hand, with heat, you're storing a very small amount of energy per atom, but you're storing it in effectively every atom in the system. And for this reason, it's very robust in the sense that we don't really care where the atoms are or how they're moving, or we have long lifetime in the sense that the only thing we're truly doing is heating up or changing the kinetic energy of the atoms, raising it, and then lowering it back and forth. In this case, I'm talking about sensible heat rather than phase change. And this is actually one of the reasons we're specifically focused on sensible heat rather than phase change. When you do phase change, you're breaking and reforming bonds. The way you break them and reform them each time now has to require some care to make sure that you reproduce the same thing in the same way and you don't build up any new layers or different microstructure or all the problems that could show up with regards to cracking the crucible or the container. And so just by heating and cooling, we, I think, are in a regime where things are quite simple for us and can have very long lifetime. You can get very high energy densities, so even with sensible heat, you can get sufficiently high energy densities to be competitive, and the costs can be low, particularly because we don't really care what kinds of atoms they are. As long as their kinetic energy goes up and down, we're able to get the energy in and out. The only reason the type of atoms really matter is their cost and to what extent they interact with the container and cause some kind of corrosion. I'll talk about that in a second. So just a simple estimate, I think this is probably pretty obvious to most people. If you want to store, for example, something like metallurgical grade silicon, the cost, swinging it over, let's say, a 500 degree C delta T, comes out around $23 per kilowatt hour electric. This is assuming a 50% nominal efficiency for the heat engine. And so this kind of cost target or initial cost number is attractive by comparison to lithium-ion batteries. This is roughly speaking a factor of 10 or more cheaper. Conversely, you could imagine going to something else like scrap iron, scrap steel. You can get another order of magnitude cheaper, down to about $3 or $4 per kilowatt hour electric. So this is where it's attractive from the standpoint of what materials you pick. And there's an interesting thing that happens with respect to corrosion, which we had not really thought about until we started this, which is that, well, let me see what my next slide is. I'll get to it here. I'll go back a second. But one of the main things that we've looked at, and I think this is a bit of insight from some of the other work we do. So I don't just work on this, work on also studying heat transfer at the atomic level, studying atomic vibration, doing molecular dynamic simulations, and so we have a little bit more materials insight than the average mechanical engineer. And so one of the things that seemed like a losing proposition from the beginning is if you want to go hot to be able to use cheap materials, one of the things you probably want to do is think about moving beyond using metal as a containment material. And so this is kind of the step change in terms of the thinking, is to move beyond thinking about some metals that you can weld together to make a container, to make piping, to make pumps, to make valves, to make whatever you want. Instead, to look at using ceramics. So you take, you can think about elements in this regime here where these are low melting metals that can be liquid at pretty high temperatures, and you can hold them in containers made out of combinations of elements in this range and this range of the periodic table to make ceramics. And the idea being that once you have these ceramics, they're covalently bonded. The bonds are very stiff. It's very difficult for them to form new compounds with these elements down here. And so our initial demonstrations of pumping and whatnot were done with liquid tin here. Now, the reason I bring this up is because essentially corrosion boils down to the idea that there's some group of atoms that would like to interact chemically and form a stronger bond with something else, or possibly release some gas or something that would have a lot of entropy with it, and so the reaction will be favored as you go to high temperature. What we found, though, and I think we'll put this in the book chapter, is there's kind of this these interesting regimes of stability. So typically, when you talk about corrosion, people are thinking about metals below about 1,000 degrees C. Generally speaking, the hotter you get, the worse the corrosion. It just accelerates the kinetics. Generally speaking, there's lots of compounds that can be formed that are very stable between, let's say, 1,000 degrees and about 1,500 degrees C. There's a lot of oxides and a lot of different compounds that can form in that regime. But when you start thinking about going, presumably, let's say, much hotter than that, if you go well beyond 1,500 degrees C, you get to this new regime where actually a lot of the materials that may be stable in around 1,500 degrees C, a bunch of ceramics actually start to lose their stability. And once you get to about 2,000 C or and above, there's actually a smaller group of ceramics that are very, very refractory that remain stable. This has an interesting effect on corrosion, because now when you go really, really hot, it actually turns out that a lot, when you have, let's say you start with silicon, you have, let's say, some impurities in the silicon. Those impurities won't be able to form any corrosive byproducts, because none of those byproducts are stable enough to stay solid at those temperatures once you get that hot. And so you can push high enough in temperature, you actually get to a new regime where it's actually difficult for things to corrode and form new compounds. And it's instead more thermodynamically stable for them to stay in the liquid phase and diffuse around as in a dilute liquid, as dilute impurities. So one of the other things so that plays an important role in the logic for how we've approached it. I'll get to our approach in a minute. Another key piece of the logic behind our system and how we've arranged it is this issue of the surface area to volume ratio. So, thermal storage, I think it's largely a concept because it's done commercially in the context of concentrated solar power. The idea here, I think everybody's probably familiar with, but I just want to emphasize it, is that if you make the tank really large, the rate of heat loss scales with the surface area, the amount of energy stored scales with the volume. So as you make it bigger, number one, the rate of heat leakage compared to the amount of energy stored starts to decrease and drops. Today they operate molten salt plants and molten salt tanks with less than about 1% of the energy stored lost per day. This isn't like an acceptable regime to be in, and so We're interested in doing essentially the same thing. When you go as hot as we're interested in, it requires some different types of insulation, which are not negligible cost-wise. But one of the key things is also, once you make it really large, the time constant, the time it takes for it to cool down, also scales with that volume to surface area ratio, and so that gets longer and longer. And so typically these tanks have time constants on the order of months, and so they can sit idle without doing anything for multiple months without freezing. So this is another important thing. So the main message from this slide is really that for our system, we're interested in making it large. As you'll see, we have the ability in this system to tune the power to energy stored ratio, or the number of hours of storage. We can tune that pretty far. But what is key and what is important is that at the commercial scale, we do need it to be big. It needs to be big. So we can't really get around that. So again, we're going with some kind of ceramic or as opposed to metal-based containment because we're going extremely high temperature. And so this is the system overview. I'll walk you through how it works, and I'll talk you through some of the design choices here. So we have 2 tank thermal storage. We're doing the liquid. Let me nominally call it metallurgical grade silicon. We're actually looking at also adding iron to the silicon. It drops the cost even more. Also has another few other interesting impacts that are useful. But let's just for as a base case talk about metallurgical grade silicon. So our cold tank is actually at 1900 degrees C. So our cold tanks, we're pushing the temperature as high as possible here, up to about 2400 degrees C on the hot side. So of course, when you want to store the electricity, you pump the quote-unquote cold silicon, which this is far above its melting point, through a heating element or past Joule heating elements. You can take electricity from any agnostic source, heat up the silicon, and put it in the hot tank. And so the idea here is this 2400 degrees C is more of a practical limit. The entire infrastructure here is envisioned to be made out of graphite. 2400 degrees C is probably the approximate practical limit for how far you can push graphite before 2 things happen. Above about 2500 degrees C, the strength of graphite starts to decrease. It's actually increasing up to about 2500 degrees C. The second thing is that the vapor pressure of graphite starts to become very substantial at these temperatures. And so those are the 2 reasons we stop nominally around 2400 degrees C. But we're trying to push the temperature as high as possible because we're trying to push the spectrum as far to the higher frequencies as possible, because we're going to do the conversion with PV rather than a turbine. And we only need roughly a 500 degrees C delta T in order to be cost effective, and we could actually go lower than 1900 degrees C. The liquid won't freeze until about 1500 or so. So we have more room to play, but this is our nominal operating condition that we envision. When you would like to make electricity again, you then pump the liquid out of the hot tank through this power conversion module, which has a number of things inside. The liquid flows through a bank of tubes, so you can think of it kind of like a heat exchanger. All this tubing is made out of graphite. In between, we have a tungsten layer. This tungsten layer is very important. I've drawn it with fins here to indicate that we could actually increase the surface area by actually putting tungsten foil to actually increase the amount of surface area. There's a reason we want to do that. But the reason the tungsten is there is effectively to act as a diffusion barrier. So this temperature range that we're operating in is so high that the vapor pressure of the graphite is substantial. And you've got something near it which is cold, which is the PV. So the PV is actively cooled, so it's near room temperature. If you didn't have this tungsten, you'd basically make an evaporator where you'd heat up this graphite and it would gradually deposit on the cold side, and you would just transfer material from hot to cold. In order to prevent that, we have some ideas on how to prevent that. But one of the key things that also goes with that is to actually put tungsten here, which has about a 2 order of magnitude lower vapor pressure than graphite does. So you want to get a running start and offset the system towards not having this problem happen by using a material that's got even lower vapor pressure than graphite, which tungsten is one of the best. I believe it is the best, or lowest vapor pressure. And it's essentially the best we can get at an industrial scale to buy tungsten foil. So all our cost estimates and things have this cost included. And so this tungsten now radiates light onto PV cells. These PV cells are not your normal PV cells. colleague of mine at Georgia Tech affectionately started calling it sun in a box, largely because we've gone so hot that it's essentially like putting the sun inside of a box. And the reason that these PV cells are not normal is because, number one, they've got reflectors on the back, so they've got mirrors, so this is key towards recycling and keeping the light that you cannot convert efficiently trapped inside the system, so it would bounce off this mirror, go back to the piping, and keep the hot side hot so you don't waste the energy. And the second thing is we're looking at using multi-junction photovoltaics, so we call them MPV cells. I'll show you later. You can see the spectrum. For the cost that you expend to grow one junction, it's not a great increase in cost to grow a second junction and actually improve the efficiency significantly. So this is the overall schematic of how the system works. We envision, as someone mentioned earlier about the insulation, particularly in this portion of the system, not necessarily over here, but particularly in this portion, filling this with krypton rather than argon, so this will help to cut the heat losses. So we're not envisioning operating this in a vacuum. If you look at this deposition issue of going from hot to cold in a vacuum, it's way too fast. It's like it's a losing proposition. I don't think that there's any way that you can keep even tungsten from coating all over the PV. So we do envision keeping this at 1 atmosphere in a gas environment. We just take the convective heat leakage hit on the efficiency. One of the other reasons that it's good to go to very, very high temperatures is we can get the PV output to outrun all these other losses. So the PV output, right, the amount of light that you have coming out of this infrastructure is scaling with T to the 4th. And so as you go hotter and hotter, you quickly overcome all the other sources of heat leakage. You've got heat leakage out of the system through this insulation. You've got heat leakage through convection across the gap, and so you're able to outrun these. These losses still exist, but those losses scale linearly with the increase in temperature, but the radiation scales with T to the 4th, and so you're able to get to a temperature range where you win. So I say all that to give you the basic concept. If I were to tell you this and you didn't know some of the other work we've done, you would say we're absolutely crazy, because there is no such thing as a pump that works at 2400 degrees C. And I'll tell you some of the other things that are challenges with this. But I think what we have done that has given us the courage to think that we might be able to pump at 2400 degrees C is that we have actually pumped at 1400 degrees C. So this is a project we did a few years ago. First thing we pumped was liquid tin. So this is the way the system was arranged. It's basically a graphite crucible with tin. Tin and carbon do not form any chemical compounds. So they work very well together in the sense that the tin is not even wetting for graphite. So you could just make an all graphite system. Our initial pump was actually made out of an aluminum nitride composite. We're now interested in making pumps that are just all graphite, but no real intrinsic issue here. Our new, I think, step forward in doing all of this was these joints. So in order to make a system like this with flowing liquid metal, you can't really make it out of all one piece of graphite, and so you've got to connect pieces, and it's the connections where the liquid will want to leak. You've got to seal them, and so that's really our big contribution here, is figuring out how to actually seal against the liquid at these extreme temperatures, and so the seals are all refractory and do not chemically interact with the liquid we're pumping as well. So that's key. The second thing is that the pump here was a gear pump. So this involves solid-solid contact, and so we saw some wear on these pump components over the course of roughly, I think, 72 hours or so. We're more interested now in doing pumps that do not have this kind of solid-solid contact or this kind of wear issue. Centrifugal pumps, for example, is what we envision using in our system. But this is a video. We were very interested. We knew if it worked, we would be the first to do it, and so we really wanted to see it. So we cut a hole in the insulation so we could look in, and in cutting a hole in insulation, we got quite a bit of heat loss. Not to be I mean, was expected. But this heat loss also was important because it also limited the maximum temperature that we could get to. And so we stopped at about a little bit above 1400 degrees C. But in principle, there was nothing preventing us from going even hotter than this. And this is why we think we can go to 2400 degrees C, particularly if we use graphite. Aluminum nitride would not work at 2400 degrees C, but graphite could conceptually work at 2400 degrees C. One of the main things that happens in a system like this is all the components grow thermally, so you get thermal expansion. And so essentially we have a bunch of hot components, and then we have a series of connecting shafts where there's a temperature gradient, it cools, and then the motor stays in the cold region. So you have a cold motor, hot moving components in the hot zone. And so one of the key things that happens here is you get thermal growth, and you would get misalignment of the pump, which could, the first few times we tried it, it broke itself apart. But there's a way to account for this. If you calculate how much it grows, you can offset it so that when it heats up, it actually grows into alignment and then operates okay. We have new designs now that don't have this issue where the growth is all axial rather than perpendicular to the rotating axis. All right, so we've also started doing some testing above 2000 degrees C, and I think this is important from one standpoint, which is, I personally was not really a believer in this concept that this system really had any chance of working until we dealt with one particular issue, which is the tank. As I mentioned before, with the pump system, you cannot make the entire pump system, all those pipes, out of one monolithic piece of graphite and cut a bunch of holes in it. The same is true for the tank. So if you're talking about an order 10 meter diameter, 10 meter tall tank, you cannot make that out of one giant piece of graphite. And so therefore, we were interested in trying to prove or see if it was possible to actually make a tank out of multiple sections of graphite that are bolted together with a seal. The key is a seal. So right at the interface between two pieces that you just mechanically butted up against each other is where the liquid will want to leak out. So it's well known, if you put silicon in contact with graphite, they're going to react, you form silicon carbide. But if you use sufficiently dense graphite, that reaction proceeds to a point where you then fill the pores, and then it stops. And then you end up kinetically limited by further diffusion of carbon through silicon to get out and make more silicon carbide. And it turns out, we're lucky, that diffusion is extremely slow, such that basically it starts reacting and then it finishes, and then it can sit there for 100 years or so without making roughly another 10 to 100 micron more of silicon carbide. So that reaction is kinetically limited, or let me say it's diffusion limited. And so one of the things we did was to try to prove to ourselves that this could work. So we use actual metallurgical grade silicon. It's only 98% pure. We built a little miniature tank, so this is only about 6 inches tall. It's got two pieces, so it's a top half and a bottom half. So right here at this seam is where the seal is. If you did nothing, if you put nothing there, this is exactly where the liquid will want to leak out, because it's two pieces that are pressed up against each other. But what we do is, and it took us a few times to get it right, but what we do is we put a piece of graphoil there, so it's a flexible form of graphite. It's all graphite, it's all carbon. So it's fine to operate at the temperatures of interest. And we essentially compress down on that seal. So when we press down on the seal, it forms a tight connection. And when we put the silicon in there, what happens is the silicon, of course, wants to react with even that graphite seal, but that reaction is expansive. And so it actually fills the gap, and the silicon carbide essentially plugs itself, and the silicon is not able to continue to get out. The silicon carbide is what essentially helps us as a seal. So we've done that with metallurgical grade silicon. We've also done it adding 50% iron. So if you put a silicon carbide coating, if you start this with silicon first, get silicon carbide on all the walls, then you can add 50% iron, and then these two can sit in contact with each other, thermodynamically stable. So it's not, you do not eat into the wall. If we increase the iron content, let's say you go to 100% iron, what you'll find is the wall will be recessed. It's actually dissolving the carbon. It gets through and starts to dissolve the carbon. And so one of the cool things about operating this hot is everything happens really fast. So you don't have to sit and wait for 100 hours to see if something's going to happen. If it's going to happen, it'll happen in a few minutes, and you'll see it. So all of these results are discussed in a paper we have in EES. Let me talk a little bit about the logic behind why we're using PV instead of a turbine. So the original incarnation of this, we actually were interested in using a turbine. We were actually interested in lower temperatures and using a combined cycle turbine to get to higher efficiencies, normally like 60% rather than 50%. And spent some time, I'll say a year or more, really trying to drum up support. If you want to get a new turbine made, at the end of the day, we would need like GE or Siemens to actually make it. And that turns out to be a very, very big barrier to deployment. Right now, the energy storage market is budding. There isn't a big enough market to really convince them to invest greater than $100 million to do the R&D to develop a new turbine system. So the new turbine would be very different than anything that exists today, in the sense that it'd be a closed cycle, Brayton cycle, would use an inert gas as the working fluid. You've also got new materials and new heat exchangers you've got to make. So now you've got compressed gas coming out of a compressor that now needs to be heated up to 1500 degrees C. So unlike how it works inside the turbo machinery itself and the expander, where you can have extreme non-equilibrium between the metals that are used for construction and the fluids that are flowing past them. The fluids can be much hotter, 600, 700, 800 degrees hotter than the actual metal gets. You cannot do that with a heat exchanger. You need the heat exchanger to get as hot as the fluid itself. So you can't think about using the same material. So this requires the invention of new heat exchangers. And last of all, there's this response time. So the response time of turbines is pretty slow. And from the MPV standpoint, there's a great advantage here. So we've gotten some good reception from people who make these cells and can make cells at the scale that we're interested in. They're very interested in a new application where they can make cells, very large areas of cells. So there's a much lower barrier to deployment. The commercial entities are actually very interested in this. It can also be lower cost, particularly if you reuse the substrates. The cost can be less than 50 cents a watt, whereas a new turbine is likely to cost $1 a watt or more. So there's some cost savings here. The efficiency is in a similar range, 50 to 55 likely, but not as efficient as a turbine could be in theory. But another huge advantage is actually the fast response time. So I didn't really talk about this. I'm not going to go back, but one of the things that was on the way we have the system arranged, you have these pipes that the silicon or the fluid's going to flow through. And we have this cavity, and the PV can essentially be dropped into the light, and it can be actuated in or out of the light. And so by doing that, we can actually ramp from full on to full off as quickly as you can actuate it, which is on the order of seconds. And so that's actually, from talking with grid operators, a really, really attractive feature of doing it this way. The idea of being able to ramp on and off at the gigawatt scale is very, very attractive from the standpoint of trying to firm up renewables that have fluctuations in their response on that time scale, and also to be able to respond in the event of any unforeseen event. There was a colleague, there was a guy I met who was a grid operator in California, and he described the process very visually. He said it's, when you're doing this process of dispatching, you have to dispatch every 4 seconds. And so he said, it's imagine trying to drive a car at 60 miles an hour down the highway, and you only get to open your eyes every 4 seconds and blink very quickly and get a snapshot of the system. And so he says, for that reason, a resource that could respond very quickly and adapt to what's happening on the grid is very, very attractive from their standpoint. Here's the reason we're interested in multiple junctions. So initial modeling predictions suggest that the difference between, let's say, here's one junction. This is just take one curve for one temperature, let's say 1900 degrees C. You can see there's overall about a 5% boost you can get overall from adding a second junction. And so this is pretty attractive. And our colleagues at NREL have come up with some interesting designs for cells that try to actually eliminate buffer layers so that we can minimize parasitic absorption below the band gap. So here's a very rough picture, simple set of estimates to try to convince you that we think we can get to about 50% efficiency. We pay a very significant penalty using the tungsten. So black body radiation at nominally, this is at the intermediate temperature for us, 2150 C is halfway between 1900 and 2400. And you get a lot of black body radiation in theory. It's like almost 2 megawatts a square meter. But tungsten's like a reflective metal. And so we get less than half of that coming out of the tungsten. So we pay a very big penalty using tungsten as the emitter, but from a reliability standpoint, I think it's our best choice. So we just accept that penalty. For the cells that we're using, only about 200 kilowatts or so would be above the band gap. One of the things that we can do to affect this is this point I made about the fins on the tungsten. So if we can increase the area ratio between the PV and the emitter, we can increase the overall heat flow above the band gap, or it's the total heat flow, it's not just above the band gap. Then the below band gap is almost 500 kilowatts per square meter. By using a highly reflective back reflector on the cells, we cut the amount of absorbed light below the band gap to this small amount here. This is assuming 98% reflectivity. The cells are, of course, far from perfect, but you get more than half of the energy above band gap converted to electricity. So we're predicting about a little over 100 kilowatts per square meter. You get some parasitic heat into the cells from the back reflector, and also the inefficiency in the cells together. We're predicting roughly about 5 or so kilowatts per square meter loss from the convection. When you add all that up, so you take the power output divided by all these other losses, you get about 52% efficiency. So we think that we can get to this range. This again is at nominally about 2150 C. So at the higher temperatures, it's a little higher efficiency. At the lower temperatures, down to 1900 degrees C, it's a little lower efficiency. But this is our nominal efficiency target. We've done some cost estimation. I'll not go through this in detail, but try to convince you that this includes everything that we can think of that you would need, including construction costs and all these other things. One of the things that's, I guess, encouraging about it is, at least there are two parts to the cost. There's the cost per unit power energy. So this is all the components that scale with how much energy you store. So the tanks, the medium, all the components that would go along with that, the construction of the tanks and the outer vessel. Then there's all the components that would scale with power. So that's the size of your heater, size of your PV, all those things, the pumps and all those things that govern the rate at which you charge and discharge. So those are all on a separate plot. And so the cost of the total system is the addition of these two times the amount of storage that you want. And so the key thing here is we've got a range of estimates that scale from our more conservative set of assumptions to more fortuitous assumptions. So we think that the cost could be in this range for the total system. The main thing to get is that the dominant cost here is, of course, the medium, which is good. So the tanks are important, but when you go large, the tanks are not the dominant cost. The medium is the dominant cost, but what's interesting and what's important is that graphite insulation we need to go this hot is also very non-negligible, and so that's also a very significant cost in our system. So playing with how much heat leakage you can tolerate, whether it's 1% or 1.5 or 2%, actually has a significant impact on the cost and also how you size the system. On the other side, whether you look at the power, one of the biggest components here for us is the cooling system and the inverter. So this presumes that you're going to convert back to AC, put it on the grid, and you've got to run, this is now a dry cooling unit, so to keep the cells cooled, a big fan cooler outside, that's actually one of the more significant costs. And so we've included all these kinds of things in our cost analysis, and at the end of the day, our projections are in this range of less than $50 a kilowatt hour electric, and down around less than 40 cents a watt on the cost per unit power. Here's a nominal depiction of what the system would look like. The pumps are envisioned to be very simple. So this is like a gigawatt hour of storage. So this is, I believe, 30 meters in diameter, 30 meters tall. The pumps are actually quite small, only about a foot in diameter, so a third of a meter or so. You don't need a tremendous flow rate to get to. So this is 100 megawatts, 10 hours of storage. So you don't need giant pumps. They're giant in the sense that the shaft is extremely long because you're going to put the pump all the way at the bottom of the tank so you can suck out the last bit of liquid. But other than that, their diameter is not huge. We're envisioning that the tank would be made out of these large plates of graphite with a bunch of holes in them. Carbon fiber composite bolts are what's holding them together with a graphfoil seal at all the seams. So with that, I'll just really quickly conclude. We have an ARPA-E project. This is a part of the Department of Energy in the United States that funds high-risk, high-reward projects. We have a project with them. I didn't really talk about this, but the entire system is held in an inert environment, so there's no oxygen around. So a really big, giant vacuum chamber that we're building this in. We have a number of different things that we're trying to prove in this project. So the pumping, the heaters, demonstrating that we can overcome this issue of the emitter evaporating, doing some cell design and fabrication and optimization, demonstrating that high reflectivity and high efficiency, and also doing some long-term testing to show that essentially we can do full charge-discharge cycles. So essentially we're trying to build the full prototype, 2 tanks, 2 pumps, all fitting inside this chamber here. So it's only about a kilowatt hour of storage. But I think it's going to force us to get through most of the key issues that we would see at scale. There are a few more that'll show up as you make this bigger, but it's big enough to, I think, deal with many of the key issues. So with that, I'll stop there. Be happy to take any questions you have.
Thank you. Thank you, Dr. Asegun.
Thank you.
Is there any question?
Thank you very much for this impressive talk. I'm concerned because you obviously know that the molten salt storage, they have a key issue with freezing of the salts in the tubes.
Yeah.
So, in your case, this freezing will happen at 14 degrees.
Yeah.
So I guess you have thought about this issue, or maybe are you considering reducing the melting point of this silicon or something like that?
So nominally we are imagining that our cold side temperature is 1900 degrees C, which is a huge buffer to the melting point. So we don't actually anticipate that we'll get close to the melting point unless you go, let's say, several days without any electrical input. So if the grid goes down for like a month, then that then maybe we'd be in danger of possibly freezing. But there's so much thermal mass stored in the tanks that even if the electricity went out and you had no additional input, as long as the system is even at 1900 degrees C, you just flow through, you just continue pumping through and keep all the piping in between warm so that it doesn't freeze in the piping.
No, I'm thinking that I believe that they use some kind of heating during the tubes and so on.
Yeah.
So if you have some failure of this heating and then you get some.
So I mean, the advantage in our standpoint is that the tubing is electrically conductive, so it's graphite, so you could locally heat if you needed to. But generally speaking, it's a bit different from CSP in the sense that our system doesn't go through the nighttime day cycle where there's a set of piping that just gets cold because it's exposed to the environment. So our entire system is shielded with insulation. There's really no open place for energy to get out, and so it's more difficult for it to cool and freeze. So once you preheat it, get it started, you would never want to let it freeze. And once you get that giant vat of liquid, you've got a huge thermal mass.
Similar to that question, if you had a pump failure, do you still have that multi-day time period where you can have flow stopped in the channels in the heat exchanger assembly?
Great point. So what happens in the molten salt plants that they do is they actually just have a bunch of redundant pumps. So that's more likely we would have even more redundant pumps because we would generally not want to ever open this system up to change anything if we didn't have to. So that's one of the advantages of the pumps being rather small and not difficult or not expensive to make. So we might, for example, build a system like this with 30 or 40 pumps that most are there just sitting there and never get used, but then get engaged one day if need be. So you'd probably keep them spinning at a very slow speed such that you're not actually pumping, but so that you don't get any stiction between any reaction that might happen on any of the surfaces, but you just leave them kind of there idle waiting to be kicked in. This is essentially the same thing they do for molten salt. So they, for example, they have, I think it's at, what do they call it, Tonopah. They have 4,000 horsepower pumps, so it's a couple megawatts. And then they have a redundant set of 4 that sit and just wait idle and don't do anything. Another one here.
If you could comment a bit on why using a mechanical pump instead of electromagnetic one.
Great question. Great question. So Electromagnetic pumping would be much more elegant, no moving parts. However, the efficiencies of electromagnetic pumps are extremely extremely bad. So we're in a regime where the amount of pumping power is effectively negligible, but this is presupposing that your pump is in the regime where you're, tens of percent, you're at 80, 90% pumping efficiency. Electromagnetic pumps are often less than 1% efficient. When you get that low, what happens is the pump itself becomes just a heater, and so you could, since we need to heat, put heat in electrically. Imagine some kind of coupled system that does that, but you'd have a serious challenge. No one's ever made an electromagnetic pump that operates that hot. Usually they have some kind of permanent magnet in them. That would have to be a full electromagnetic version with like all tungsten wire. You'd have a lot of trouble insulating the tungsten wire from itself to wrap and make coils. It would just be a nightmare from a fabrication standpoint, but not totally infeasible, other than the fact that I think the pumping efficiency would be so low that you'd have to treat the pump as the heater.
Next time we'll get 2 microphones. What's the limiting factor that keeps you from letting the density gradient between the hot and cold side do the pumping for you?
I've never thought of that. I don't know. I'd have to look at that. That's an interesting thought. It might be smart to see if there's a way to arrange this system such that you could utilize that in the event of like a bunch of failures somehow. There's another option as well, which is because it doesn't take a whole lot of pressure to push through all that piping, it's just friction losses.
Right.
You can also increase the pressure in one of the tanks and push on the top of the liquid level and force it over to the other tank and go back and forth. So there's another pumping option that actually doesn't involve any hot moving parts. You could have an external compressor and push on the liquid surfaces, because the beauty here, right, is you're not actually continuously circulating in a circle. You're going back and forth. And so because you're going back and forth, you can push on one side, push on the other side, and go back and forth this way.
The microstructure of silicon inside the refractory container or tubes.
Yep.
There are many pores, and can you explain the reason for this porosity inside silicon, solidified silicon? Yes, a tank, probably in tubes. And another question is, do you observe silicon carbide particles inside due to the movement of molten silicon for a long time? It's so extremely high temperature.
So it's difficult to say because we can't look at it when it's hot. We see it when it cools, but it's possible that those particles formed on the cooling event. So here you can see some silicon carbide, and there's silicon carbide in the silicon as well. Small particles, but it's difficult to know whether or not they were there when it was hot, or if they was just dissolved in the liquid, or if they formed upon freezing.
Or maybe detached during liquid metal movement.
Possibly, yeah. We have
so
taken.
Then you produce something like slurry.
Right, and we've done a few thermal cycles of these materials to see that it's not like the silicon carbide comes off and then it starts consuming more. That doesn't seem to happen. So whatever the silicon carbide layer is, it's rather adherent. And we've done tests with a number of different grades of graphite, so it really depends on the pore size, the pore amount of porosity, and things like that. So where this matters most is in the tank, because you'd like to use the cheapest form of graphite you can that still works. And so one of my students is looking into that carefully to see what exactly. You mean here? Yeah. Oh, this is in the liquid, these voids? Oh, these voids. These voids seem to happen probably on the cooling event due to the expansion and the way that it actually freezes. But we don't know. We don't know the origin of these gaps. Say again?
So maybe some gases product, but I don't know.
I doubt it, because this has been sitting in there for forget how many, maybe an hour or more. I don't know that there's any gases left. And they're also, deep down in here.
So how did you prepare the, let's say, the tank before introducing silicon? It was like degassing of the.
No, actually, we don't do anything. We use the materials as purchased.
Okay.
Because we want to see if there is some problem that would arise with doing that, right? Do they require any subsequent processing? And it doesn't appear that they do.
Okay, thank you.
Is there any question? Okay, no, we thank our speaker.
Thank you.
Well,